Tier 1. Game engines. A game engine is a program that makes the development of video games easier, containing a set of many recurring systems that almost all types of games need, like physics, rendering, pathfinding, UI, and more integral things you will need to write again with each game you make. There are many game engines. Big studios tend to make their own proprietary engines, like Rockstar's Advanced Game Engine, Valve's Source, or EA's Frostbite. These can't be used by any person or require some sort of license and are focused on developing a very specific type of game. So you have other popular and general purpose game engines that are available to the public, like the Unreal Engine, known for its impressive graphics and bleeding edge features, Unity with a broad asset and tutorial ecosystem, and Godot with a thriving open source community. There are other engines, frameworks, and platforms aimed at specific niches, like Scratch, making development easier with a visual programming language, or RPG Maker that contains many tools for the development of RPGs. Some people even create their own engines, even though I wouldn't recommend it for most projects. By the way, if you're curious, this is Project Neon Wilds, the survival sandbox game I'm working on. It was previously called Project Shutdown, but people were getting confused, so I changed the code name. Still, it's the same game about surviving in a procedurally generated post-apocalyptic city with emerging gameplay, stealth, different combat types, natural disasters, and base building. It's in pre-alpha, so things will change. I'll show some development footage throughout the video to explain many of the concepts of this Iceberg better. Subscribe or follow me on Blue Sky to see more updates. I appreciate your feedback. Thank you. Framerate. Monitors can't really display video, so what they do is create the illusion of motion by drawing many frames quickly. The frame rate measures how often this occurs, and it tells you how smooth the output will be. The standard used to be 30 frames per second to be considered playable. These days, it's supposed to be 60 and even higher, like 144 plus in competitive games. Most monitors have a refresh rate of 60 Hz, so you would need one with a higher refresh rate to actually notice the difference. But there's more to frame rate than just smoothness. Most games that need to run some continuous logic do it every frame, including checking for input, physics, and other things. This is when different frame rates can become an issue. If your computer is powerful enough to render more frames, these functions will be called more often and can break a lot of things. One of the most infamous examples is GTA 4 and many older games that never received patches. They expect you to be running the game at 30 FPS, causing bugs like exaggerated physics or broken mechanics at higher frame rates. To help with this, engines often expose a delta variable, the amount of seconds it took to render the last frame. If you multiply a value by delta, it will be mostly consistent regardless of frame rate. But sometimes even that's not enough, which is why most modern engines have a fixed processing frame rate for physics and other things that need consistency. Predatory game monetization. There are many ways to monetize a game aside from just selling it. You have DLCs, aka downloadable content. DLCs are not bad by themselves and there are very good ones, but some companies absolutely abuse them, like EA with The Sims 4. Then came microtransactions, small in-game purchases usually for cosmetic items. Other games give people advantages by paying, which is known as pay to win. Then came loot boxes, where instead of buying a specific item, you pay for a randomized chance at getting it. Some countries have banned them because it's basically gambling. And live service games take this further by designing the entire game around an ongoing monetization structure, like Fortnite with season passes, time-limited content, and other strategies with the goal of keeping you spending money and never letting the game die. AAA, AA, and Indie. These are labels defined by a game's budget. AAA games are the blockbusters with hundreds of millions of dollars in development and marketing, made by large studios backed by major publishers. AA games are the middle ground, more polished and budget than an indie project, but not as ambitious or expensive as a AAA production. And indie games are made by independent studios or developers, with full creative control but usually with far fewer resources. The lines are blurring as games like Expedition 33 have won awards like Best Indie Game because it's technically made by an independent studio, but still with millions of dollars behind it and outsourcing a lot of the work. In some cases, indie games can earn more than a AAA game, so it's kind of a controversial categorization, and you could argue that it's outdated. Mods. Mods are unofficial modifications of a game made by the community. They can add new features, content, UI improvements, support more languages, or in some cases, fix bugs that the developer never bothered to patch. Right, Bethesda? Some of the most influential games in history actually started as mods. Counter-Strike, Dota, Team Fortress, Gmod, or PUBG. Mods have also kept games alive for decades after the official support ended. Many companies are hostile towards modders, like Nintendo or Take-Two, which is interesting considering how much mods extend the lifespan of a game. Crowdfunding. It's a way to obtain funds to be able to complete a project. You set up a campaign, a goal, and optional rewards for those who donate a certain amount of money. Many games had a successful campaign and eventual release, like Undertale that had a goal of $5,000 but managed to raise $50,000 and ended up becoming one of the most popular and critically acclaimed indie games. But many other projects don't reach their goal, like Five Nights at Freddy's. Yeah, there was a crowdfunding campaign, asking for $10,000 and not getting a single dollar. But the game still came out and became one of the most popular indie franchises, even having movies, proving that maybe not all projects need them. In some cases, crowdfunding campaigns can be controversial, as not all developers actually deliver what they promised. Early access. This is a funding strategy that lets developers sell a game while it is still being developed and unfinished. It's ideal for games in a playable alpha or beta stage, as it can be very useful to gather community feedback and funds to keep developing the game and release a stable version eventually. One of the pioneers of this concept was Minecraft. That is the best-selling game of all time and started as an indie game developed by Notch. Steam has very loose regulations about this, making it possible that a game can remain in early access forever, and it's technically okay, which is when many people think twice before buying one of these games, even though this is obviously not the case for all of them and many are actually finished. Steam has already added banners to let people know when was the last time a game was updated. Early access can be helpful for indie games, especially ones with an episodic or non-linear structure, but I also get why some people just don't like it. I don't know, what do you think about early access games? This is not just a question for engagement, I genuinely want to know, as I'm considering releasing my game as an early access. Not now, of course, but eventually. I don't love the idea, but realistically, it could help a lot because I'm a solo developer. Game leaks. It has become common for games to leak, either in the form of characters, story, or mechanics leaks, or in some cases, even the full source code, builds, or assets. The biggest gaming leak so far is definitely the GTA 6 leak that showed an early build of the game back in 2022. People criticized it because it looked unfinished. No way. There are other historical leaks like Nintendo's Giga Leak, Half-Life 2's Dark and Gritty Beta, and The Last of Us Part 2 leaks. Unfortunately, leaks can often cause a lot of damage to a studio's reputation and can lead to games getting delayed. Asset flips. An asset flip is a game made by taking existing paid or free asset packs or code, assembling them without modifications, and putting the result on Steam for sale, leading them to often have mismatched art styles, no level design, and it looks like a cash grab. Asset flips were pretty common, and I'm sure there are still many of these out there. And there was even this game called The Day Before, an alleged survival MMORPG that managed to become the most wishlisted game on Steam, having some impressive graphics and technology, but when it actually came out, turns out it was a downgraded, buggy mess made entirely with asset packs, from the sky to the map and systems. Some people claimed it was borderline a scam, and the studio ended up removing the game after a few days. I know that it sucks, but the fact that it's lost media makes me want to try it to see how bad it truly was. Now, I'm not saying that using asset packs is bad. I have used a few assets for my game, even though they're a minority, and I do make most of them myself. I think the key is to modify assets you get to fit your game. I mean, I'm sure bigger studios use asset packs too, and they can save a lot of time, as long as you use them correctly. Disastrous launches. Every few years, the industry delivers a launch so catastrophic that it becomes part of gaming history, like No Man's Sky that promised a vast universe with multiplayer, complex ecosystems, and endless variety. When it was released in 2016, it had almost none of that. The backlash was severe, and Hello Games had to spend years patching the game and adding most of the content they once promised. Cyberpunk 2077 is another recent example. After years of hype and development hell, it launched in a state where it was essentially unplayable on consoles, and many of the things the studio promised weren't there. Sony pulled it from the PlayStation store, and CDPR had to issue refunds and spend many years fixing and polishing the game. It's become one of my favorite games of all time, and clearly an inspiration for mine, not including the bugs. And while I'm excited for Cyberpunk 2, I will definitely not pre-order the game. Tier 2. Downgrades. It's very common for studios to reveal a game with a cinematic or gameplay trailer that shows an idealized version of the game. The controversy comes when the final product looks significantly worse than what was shown in the promotional material. Now, I'm not saying this is intentionally misleading. In some cases, maybe the game did resemble the trailer more closely, but as development progresses, performance may degrade and developers might be forced to remove or tone down some of the aspects of the game. That's called a downgrade. There are many examples of this, half of which are courtesy of Ubisoft, but the first one that comes to my mind is the Watch Dogs 1 downgrade. In the announcement, you could notice many advanced graphics and effects for the time. When the game actually released, it didn't have these elements and people were very disappointed. On the other hand, some studios like Rockstar are known for their trailers being in-engine and actually representative of the final product, which is why people get excited when they release a new trailer instead of being immediately suspicious. Upscaling. This is a technology that renders the game at a low resolution and uses an algorithm to reconstruct what it would look like at a higher one. It's usually faster than actually rendering at that native resolution. The most popular options are AMD's FSR and Nvidia's DLSS. DLSS uses a dedicated AI model to improve the quality of its upscaling. They can be complemented by enabling frame generation that creates fake frames between real ones to boost the apparent frame rate. This can introduce input latency and visual artifacts, and not all games support it. Upscaling has slowly become more controversial, not because it's a bad technology by itself, but because many developers now essentially require it to make their games run acceptably. Graphics card companies also love to show benchmark numbers that are technically using upscaling without making that obvious upfront. Generative AI in games. This is the ongoing controversy about using AI to generate assets like textures, models, voice recordings, and music, or other aspects like code and script writing, as it could speed up development and lower costs in theory. One of the main arguments against it is that the way Gen AI works is by scraping the content of millions of artists without their consent, so it could be considered as a way of plagiarism. AI could also be used to replace workers, and that's without mentioning the environmental impacts it has. Some games have already been caught using AI assets, including voice commentary in the finals, placeholder art in Expedition 33, and assets in Crimson Desert. Nvidia recently showed DLSS 5 that basically applies an AI filter on top of a game to make it look more realistic, hallucinations included. This technology has already faced a lot of backlash, even if it hasn't come out. People say it looks uncanny, it ruins the artistic vision of the developers, and seems like you need two 5090s to run it. Google announced an AI system called Genie that generates interactive environments from a text prompt in real time. It's limited to 60 seconds of gameplay, it runs at 720p and 24 FPS, has no coherent game design, and it's currently available only to Google AI Ultra subscribers. And there's Ubisoft too, that has been trying a technology using LLMs that lets you talk with NPCs as if they were humans. Even if AI could be helpful in certain aspects of game development, I don't think any of these technologies or their implementations are precisely useful. They look more like a prototype or a desperate attempt to convince shareholders that this is game-changing. We know that they're not precisely the brightest people on Earth. Game cheats. People always find a way to cheat in games. I actually don't mind if people cheat in single-player games. I mean, they've already bought the game. Programs like Cheat Engine are used for this and let players change values or bypass sections. The problem comes when people cheat in multiplayer games, as it's not fair and it ruins everyone else's experience, especially in competitive games. Thus, companies tend to implement anti-cheat measures, from detecting installed programs to modified game files, visited websites, input, and more. The most controversial implementations, like EC Anti-Cheat, can even run at the kernel level, the deepest level of the operating system. Of course, this is extremely privacy invasive, doesn't work with all systems, and has potential security implications, some of which have already been exploited, but I talk more about this in the cybersecurity iceberg. Game development events. There are many events focused on game development. You got the annual Game Developers Conference, where developers from many studios share their own experiences and knowledge about different aspects of game development, like game design, mechanics, playtesting, behind-the-scenes footage, and more. Many conferences are available on YouTube, making it a very valuable resource for anyone learning game development. I've watched some of these myself, and they've helped me a lot. There's also game jams that are events where developers make a game from scratch, usually within a few days max, around a specific theme. Because art takes time, placeholder or free assets are completely normal. Many developers recommend them as the single best way to actually finish something with a tiny scope. Some of these prototypes end up becoming foundations for successful games. And we can't forget about the Steam Next Fest, that is a triennial event promoting upcoming games. I've heard it's still a great way to get a lot of wish lists. I would like to participate someday, but my game's demo is not ready yet. Development hell. It's a situation where a game or any other project remains stuck in early development or with constant big changes like rewrites for a long time. This can be due to mismanagement or technical limitations, some of the most popular examples being Beyond Good and Evil 2, Duke Nukem Forever, or Metroid Prime 4. A common symptom of development hell is scope creep, when you fall into the "I'll just add one more feature" mindset. Every feature has side effects and requires polish, so your scope quietly grows until the game loses its identity or you burn out. I think it's happened to everyone. I'm not saying it's bad to add new features, but I think it's worth asking yourself whether a new idea actually makes the game better and complements the existing mechanics, or whether it just makes it more complicated or dilutes the experience. Another common situation, especially with beginners, is tutorial hell, where you find yourself not being able to progress because you rely on tutorials, so you don't understand what you're implementing or why it works, and eventually you'll want to do something there's not a tutorial for. Same with relying too much on AI. It doesn't really think by itself. If you don't know what you want to implement or why you want to do it or whether you should even do it in the first place, it'll lead you in the wrong direction so easily. I would personally suggest to avoid tutorials and learn mostly by reading the documentation. It's not as boring or hard as it looks, and it'll help you to develop your critical thinking skills, which is the most important skill game development requires. Out of bounds. All games, regardless of how open the world is, have limits you can move past. Games mask these in different ways. GTA uses an infinite ocean, other games use mountains or invisible walls. Some are more creative about it. It's possible for players to escape the bounds using glitches, getting access to content that was never meant to be seen, like unfinished map sections, cut content, or just the void that exists behind the scenery, like a scrapped version of Mexico in Audio 2, or the slender de-arrival section where the game detects you're out of bounds and has the character break the fourth wall to kill you. Out of bounds exploration tends to feel uncanny due to bugs, doing something you're not supposed to be doing, and partly the liminal theme of areas that were never finished and thus are uninhabited. Playtesting. Playtesting is playing a game not for fun, but to find bugs and see what can be improved. We as developers are too familiarized with our own game, so we need players to give us the perspective of an outsider to know if our game is actually fun. People say that there's nothing more humbling than seeing a player struggle with a part that you thought was easy to understand. Valve famously uses playtesting throughout the entire development process, including psychologists to analyze behavior and see whether the game they're making is actually successful at what they intended. Open betas serve a similar function, releasing an unfinished build to thousands of players to catch things that internal testing never would. Content. Content gets cut all the time. Characters, story sections, mechanics, entire areas, and more. It could be due to deadlines, creative differences, redundancy, technical limitations, or the scope was just getting too big. Many things that were cut can end up returning in sequels or expansions. A wiki called The Cutting Room Floor compiles cut content from games, and it's a fascinating rabbit hole. Some games hide traces of cut content deep in their files, accessible through decompilation or data mining, a process where you scrape through game files and code to find things that weren't used or that could tease upcoming content. Dev rooms. These are simple test spaces that developers build when prototyping a new mechanic or when they haven't started actual level design yet. They tend to be basic rooms with props scattered around to test scale, collision, or gameplay. Some devs leave them in the game by accident, and players somehow find a way to access them, like in Fallout 76, where players found a dev room containing all items in the game and exploited it to get free infinite loot. Anti-piracy measures. Despite being illegal and uncommon these days, game piracy is still an issue for many companies, so they came up with many ideas to prevent this, usually in the form of digital rights management, technical measures that prevent unauthorized copying or sharing of a game. The most infamous example being Denuvo, that uses complex obfuscation techniques that can degrade performance, leading to some developers removing it later, and it has still been cracked in a few instances. Physical physical copies of modern games have found a way to add restrictions too, and often require an internet connection to verify ownership or an update anyway. Nintendo's game key cards go even further, as they're physical but have no data and require a download. Some developers get creative with their anti-piracy measures, like in Arkham Asylum, where pirated copies disabled gliding, making playing the game a hassle. GTA 4 applied a drone camera effect that made it basically unplayable. Pirates wouldn't realize that it was intentional until they asked for help online. These soft sabotages are often more elegant than hard locks and significantly funnier. There's also a whole genre of creepy anti-piracy screens that became very popular a few years ago. Of course, most of these aren't real, but it's still interesting. "3D modeling pipeline." Every artist has a different workflow, and it depends on what your art style is and what you're modeling, but it usually goes something like this. A 3D model or mesh is made out of polygons. Objects with more geometric detail usually need more of these. You can start by using a high poly mesh and sculpt detail by moving its vertices, and then bake this detailed model to a lower quality version with normal maps. This is more common if you need to bake textures or characters that usually need thousands of polygons. But you could also make low poly models from the start if the object you're making is a simple prop without much geometric detail. In order to apply a texture to your model, you need to go through a process called UV unwrapping that projects a 3D model onto a 2D plane in order to map parts of a texture to mesh coordinates known as U and V. You do this by marking seams, edges where you don't mind the texture being visibly cut. You can also apply textures by using texture painting if you need more artistic control. If you need to make a character's limbs move, it's necessary to make a skeleton and use weight painting to indicate how much influence a bone is going to have on surrounding vertices. Incorrect weight painting can distort characters, and it's usually very noticeable. During this entire process, it's helpful to have access to parts like arms and legs, which is why artists usually design characters with a T-pose. It's also used as an animation fallback when something breaks, and that's why sometimes you see NPCs doing that. In some cases, it might be necessary to go through another process called retopology. It's basically remaking a detailed 3D model but using far fewer vertices and simplified geometry. Of course, all of this is a lot of work. There are many tools that can help you to automate some of these parts, like Mixamo for automatic skinning, rigging, and animations, or UQ Paint to make Blender texture painting easier. If you know more tools, please leave them in the comments. Shaders. A shader is a small program that runs on the GPU. GPUs are better than CPUs when it comes to certain heavy operations, which makes them ideal for controlling how graphics are rendered. Shaders originally only handle shading, hence the name, but they've evolved. Modern shaders can handle PBR, physics-based rendering, which uses multiple textures to represent a surface's properties more accurately, with textures for roughness, ambient occlusion, or a normal map to fake surface detail without real geometry. They can also be used for animated grass or water, or more expensive compute operations and post-processing effects. They're great, but they have this reputation of being hard to understand and requiring a lot of math. One big downside is the shader compilation stutters. Games need to compile shaders for your specific GPU, and if a game doesn't do this up front, it'll do it on the fly the first time it encounters that shader, causing a noticeable stutter right in the middle of gameplay. You can pre-compile shaders to get rid of the stutters, but they can also take a while to finish. Physics engines. Physics engines are a core tool in game development, and there are many of them, like the Jolt physics engine or the Havoc engine. They allow you to check for collisions with raycasts, used for shooting in FPS games and for environmental detection, shape casting, that is the same as raycasting but with a custom shape, or trigger volumes that can be used to check if the player is in a specific zone or to define attacks with hitboxes. Physics engines also have many types of physics bodies that simulate physics for different purposes, and they let you filter between collision types by defining different layers. Rigid bodies are affected by forces like gravity and can collide with other bodies. They're used for props that can be moved around and that should have a consistent shape. If you want to move a character via code with custom velocity values, you would use a kinematic body. There are static bodies that define a collision for other body types and they can't be moved around. In some engines, you have soft bodies that are like rigid bodies but that can be reshaped at runtime. It's useful for jiggle physics, clothes, and other deformable surfaces, but they can be quite expensive. You can combine these with hinges to create effects like doors or chains, or use ragdolls that use a set of rigid bodies to make a character follow the physics simulation, and it's used to create animations like characters dying, reacting to explosions, or being shot. Lighting. Lighting is very important in games, and it can even transform a scene. Engines have different types of light sources, like directional lights used to simulate the sun or moon, point lights for candles or circular lights, spotlights for flashlights and cone-shaped sources, and in some cases, area lights that provide rectangular light sources you could use for displays. There are many ways to simulate light in games. There is baked lighting, where a game pre-calculates lighting, shadows, and indirect light and stores them as textures. It's really fast to render at runtime and offers a really good quality, but has significant limitations as nothing can move and requires to manually bake scenes every time they change. Still, it can be ideal for linear games or sections where the map is not supposed to change. But if you need things like a day-night cycle or light sources that move, you probably want to use dynamic lighting that calculates light sources and shadows in real time. It's more expensive but way more flexible. Dynamic global illumination takes this further by simulating how light bounces off surfaces, adapting to changes in geometry. It makes a huge difference, but it's also more expensive. The most realistic and slowest method is real-time ray tracing. It traces a ray from the main camera to calculate lighting, reflections, and shadows. It's similar to how light works in real life and bypasses limitations traditional methods have, providing more accurate refractions, especially for glass and mirrors, and improved reflections that work regardless of whether they're visible on the screen, unlike SSR. It's a pretty cool technology, but it can easily tank your FPS depending on how powerful your GPU is, and many people don't notice enough of a difference to justify the performance cost. Level design. Level design is specifically about the layout, pacing, and flow of a level, but before any of that gets built with final assets, you have to create what's called a gray box, white box, or blockout, a space made entirely of placeholder geometry with no textures. The point is to test spacing, flow, combat, and feel before investing in finished art. If a section doesn't work, you can just move a box instead of rebuilding a detailed environment. It also prevents you from getting too attached to something before you know it works. Modular kits are another common approach of building levels. It's a set of reusable, pre-built pieces that snap together to construct environments quickly while still maintaining visual consistency. It's what I and many other developers or studios use to make maps quickly. Game design. Game design is one of the most misunderstood aspects of game development. It's the design of rules, mechanics, feedback loops, and systems. Basically, the theory of what makes playing your game actually fun. All of this is compiled in a game design document. It's useful for keeping large teams on the same page during development, and it's also useful to define scope. To prove that your game is indeed fun and worth making, you would create a vertical slice. That is a fully polished section of a game built specifically to demonstrate the final quality target. Some developers opt for a horizontal slice that covers many systems at a low polish to get a better idea of how they would work together. It's common for one of these slices to end up becoming a demo. UI and UX. The user interface is the set of visual elements the user interacts with to perform certain actions. It includes items like buttons, sliders, icons, and progress bars that are shown in a menu or as part of the HUD, a persistent overlay that shows the most important information in real time. There are many aspects to game UI design, like ensuring fonts have consistent sizes and hierarchies, that layouts support multiple screen sizes, aspect ratios, input devices, considering local and how it might affect the amount of information shown, or ensuring that the color palette used provides good contrast. Too many UI elements can be overwhelming and even distract the player, like in certain games with 1,000 map icons, or where the player keeps looking at the minimap more than they look at the game itself because it's just too useful, which is why some developers prefer using diegetic UI as much as possible, as it provides another level of immersion and can even introduce new mechanics or lore. It's a type of interface that is supposed to exist in the game's world, like the health bar in Dead Space, ammo shown on the weapon itself, or games with physical screens or maps a character interacts with. They're considerably harder to implement, and contrast or accessibility can be compromised, so that's why most games don't bother having it. UX, on the other hand, is about the quality of the user experience a player has when interacting with your UI. Games with a good UX manage to be efficient and prevent the player from having to spend a lot of time lost in submenus. If using your UI feels like a chore, it's very likely bad UX. I would like to recommend this website called GameUIDatabase.com that compiles an ever-growing list of user interfaces in games. As a developer, it's incredibly useful when you need references for your UI. Animation techniques. There are many ways to create animations. First, let's mention the traditional methods of creating predefined animations. Frame-by-frame animation is still common in 2D games, and it involves drawing every pose manually, and is usually saved to a single file called a sprite sheet. It requires a lot of manual work, skill, and time, but gives full creative control to artists. 3D games rely heavily on rigged characters, skeletons with bones that form a mesh and are animated with keyframes. What most big games do is to use motion capture to record the movement of real actors and then apply that movement to a 3D model, making it look natural. Most games mix animations in real time, as it can save a lot of work and look better, like when a character is crouching and shooting at the same time. You combine the regular shooting animation with a single crouch pose, or you can also use it to smooth transitions between animations. To make animations more convincing, you can use root motion that uses the movement of the animation itself and applies it during gameplay instead of having a constant linear speed that causes characters to look as if they were sliding. In game engines, these animation setups are defined as graphs, which can become extremely messy and hard to scale. This is a problem motion matching aims to solve by continuously searching a large database of animations to find the best match that will make a character follow a desired path. It produces more natural results, but it requires large amounts of motion capture data and a lot of memory. The final technique is procedural animation that generates animations in real time using algorithms or physics simulations. It can be useful to have more variety, accuracy, and safe work. The most common form is IK, or inverse kinematics. It lets you manipulate chains of bones starting from the target instead of the root bone, and it can be extremely useful when animating, or if you want to have characters whose feet adapt to the environment's height dynamically. Things like ragdolls or jiggle physics can also be considered a form of procedural animation driven by physics simulations. Sound design. Sound design includes creating and integrating audio in games. It starts by getting source files via recording your own sound, using stock libraries, or creating them with virtual instruments. Good sound effects can improve a game's immersion, define a mood, and give useful information to the player, like notifying them about enemies nearby even if they're not seen, feedback after an action, or sound cues during combat. Many commercial games use middleware like Fmod or WWise. They're audio engines that help designers define how sound behaves and interacts with the environment. Common examples are crossfading between tracks, making music adapt to a boss fight, or to have variations based on the distance from the player. Pathfinding. If you move a character only by calculating the direction to a target position, you'll eventually notice that it will bump against walls and other things because it doesn't account for the environment. This is when you'll need to use pathfinding to get the shortest valid path towards a point. Most games use the A-star algorithm for this, and navigation meshes, simplified polygon representations of walkable surfaces baked before the game runs. AI characters shouldn't query this mesh every frame because it's expensive, so what most games do is to spread these calculations across many frames. Pathfinding includes navigation links that are a way of defining connections between navigation meshes. It's used to let characters be able to jump between points, climb ladders, or vault. In some cases, you might have destructible environments, so what games tend to do is to rebake the navigation mesh at runtime. It's usually better to have many smaller nav meshes instead of a single huge mesh, as it allows you to bake only the smaller portions that changed quickly. Game feel. It's about the feedback a player gets when interacting with a game, like that satisfying sound effect you hear after a headshot or when picking a new item, that combination of animations, particles, and screen shake after a punch or an explosion, the little animations the UI has when you click on a button, the vibration of a controller when driving a car, or tiny quality of life features like coyote time to let the player jump milliseconds after falling, or highlighting the crosshair when you aim at an enemy and showing a subtle effect to let you know that they're dead. A game with good game feel makes your actions feel impactful and keeps your game engaging, even giving it a personality. Games without a good game feel often feel flat or like they lack something. VFX. There are many ways to implement visual effects in game development. Most engines have particle systems that let you simulate effects with hundreds or thousands of elements by using a mix of meshes, textures, and movement based on physical properties like gravity or speed. This is what games can use to create effects like fire, smoke, raindrops, or trails. In some cases, you can even combine these with sprite sheets to create animated particle textures or make particles able to interact with colliders. Games traditionally use sprites with transparency to create effects such as smoke, but there are newer techniques like volumetrics that instead of using a smoke texture that always faces the camera, it simulates an actual 3D volume with depth. Because it's quite expensive, games use a very low voxel resolution, but even then, it can be used for things like more convincing interactive weather effects or clouds too, like the ones in CS2 or RDR2. 3D transparency in computer graphics can be quite expensive because the game is forced to draw things many times, and it can often lead to overdraw or sorting issues with alpha blending. So that's why you usually only see it in certain effects, or used in the form of alpha testing for those use cases that need basic, complete transparency in certain regions, like foliage. Some developers prefer using the screen space texture that is like a screenshot of your game to create more complex effects using shaders. This allows you to create translucent water distortion effects, glass, or even more complex post-processing like screen space reflections, ambient occlusion, etc. An effect that has become increasingly popular in games is parallax occlusion mapping that shifts the UV coordinates of a texture to create the illusion of depth in a single plane. This is very useful for things like bullet hole decals locales that appear to have depth, materials with parts that should have different heights, or for interior parallax mapping that creates the illusion of having detailed 3D interior rooms without having any real geometry other than a quad. I'm sure there are more techniques and impressive effects out there. These are just the main examples I've noticed in modern games. Randomization. In games, sometimes you need something to be random in order to give it some variety or make it less predictable. True randomness in computers is actually quite hard, so the way most games do it is by having deterministic algorithms called pseudo-random number generators that produce values that look random but are reproducible from a known starting number called a seed. If you use the same seed, you'll get the same exact results. These random numbers can be used to define many things, like the probabilities of certain items being dropped or for random events in the game world. You can use weighted random selection to favor some results. Some players in the esports or speedrunning communities tend to complain about RNG, as they argue that games using it too much favor luck instead of skill. Randomization is also used for other aspects of game development in the form of noise textures that use random values to create continuous, organic-looking patterns you can use to simulate imperfections in materials or height differences in terrain generation. Instead of designing content by hand, procedural generation uses algorithms to create it automatically. This can apply to anything: terrain, dungeons, enemy placement, loot, etc. You can do it at runtime or to aid during development. At its best, it produces virtually infinite variety and replayability, like in Minecraft. At its worst, it produces endless repetition that feels empty, like in Starfield. Sandboxes and roguelikes tend to benefit from it, while narrative-driven games usually don't. Game patterns. When making a game, you'll often encounter many problems that other developers have already found solutions for and that can be reused across projects. This is known as a game programming pattern. You can find many of these in this website known as gameprogrammingpatterns.com. It's extremely useful. Some of the patterns I love and use in my project are composition, where you define functionality as pieces that you can attach to any entity. That way, you can reuse a Herbox component for the player, only a few NPCs, enemies, indestructible props, even if they have nothing to do with each other. The observer pattern that allows an object to listen to events without needing tight coupling. Many engines already have built-in features for this, like Unity events or Godot signals. And the state pattern, where you define many states, but an object can only be in a single state at a time, defining custom transitions between them, making it useful for things like player movement or UI states. The opposite exists, and it's called anti-patterns that are known bad practices you should avoid, like relying too much on global state or singletons, because it introduces dependencies and can lead to the creation of god objects that handle everything, or hard-coding values with magic strings or numbers embedded in a script, when you should be using a variable or constant instead. Patterns aren't like a Bible or anything. You should only use them depending on what you need. Some of these might not be the best solution in every scenario. Save systems. Save systems take care of serializing information and saving it to disk, but this is not as easy as it seems, and it often requires handling different data structures that can be nested, converting different data types, handle migration, different versions, backups, and data corruption. Games usually only save essential data, and when loading, they recreate the game state by using saved or inferred values. It's technically not a perfect recreation, but it only has to be good enough for things to work. You also have to choose a specific format. You can save the data in a text, human-readable format like JSON or XML, but then it becomes easier for players to modify their save files. You can save the data in a binary format, but then it becomes very hard to debug, even if it drastically reduces file sizes. That's without keeping in mind cloud saves or other more complex online features. Tier 4. Debugging. This is the process of finding what causes a bug and fixing it. It's not as simple as it sounds, it's more like investigating a murder you didn't know you committed, when you don't know where it happened or how. Engines provide tools to make this easier, like breakpoints that pause execution at a specific line so you can inspect the current values. Profiling tools let you see what parts of the game take longer to process so you can optimize them. Debug meshes visualize invisible things like raycasts, collision shapes, or IK targets. And debug consoles let you query or modify the game state at runtime. Cheat codes were originally developer debug tools that players discovered by accident, and some of them became iconic, like those GTA cheat codes you have in an old notebook. In some cases, games can use unit testing to check that isolated parts of the game are working correctly, and this can be automated to catch as many bugs as possible. NPC AI. Developers have come up with many approaches to make NPC AI. One of the oldest and most basic ones is using finite state machines. A character has a set of predefined states, each taking care of doing a single thing. States can have transitions between them, so you can go from a patrol state to a combat state when an enemy sees the player, and when they lost sight of the player, go back to the patrol state. State machines are simple, effective, and easy to debug, but are prone to an issue called the state explosion problem that refers to the amount of possible transitions between states increasing considerably the more states you have, which makes them very hard to manage when you have a large number of states. Some workarounds exist, like hierarchical state machines that allow states to have sub-states, so organizing them becomes a bit easier. Examples of games using state machines for AI are the Batman Arkham games and Doom. Sometimes this is not enough, and that's when you could use behavior trees. These are similar to hierarchical state machines, but solve the state explosion problem by not having explicit transitions at all. Behavior trees break behavior into small individual actions rather than entire states, and they run them based on priority and whether a condition is true. For example, an enemy can be running a patrol sequence normally, and when they see the player, the combat sequence with a higher priority runs because its condition of seeing the player is met, overriding the patrol sequence. When the condition stops being true, the tree will naturally fall back to patrolling without defining any explicit transitions. Behavior trees are way more flexible, reusable, and scalable than state machines, but they can be messy, slower, and harder to debug. Still, they're basically the standard for AI in most modern games, including the Halo series, Alien Isolation, Hitman, and Project Sunvoid. Another architecture is utility AI that assigns numerical scores to possible actions based on context, and the NPC picks the one with the highest score. It makes it so that behavior isn't entirely predictable or predefined. It's used in The Sims to dictate what actions a character should perform based on their needs and their importance. Finally, there's goal-oriented action planning, where the AI has goals and finds sequences of actions to achieve them, similar to how a planning algorithm works. It's used in games like Fear to create AI that seems organic and adaptable, but it can be expensive and more complex to implement than other architectures. Many of these can be combined. In my game, I switched from state machines to behavior trees with utility AI, so most of the actions are defined in a behavior tree, but characters will re-evaluate what is the best item in their inventory according to the context, equip it, and based on that, they will run different branches. It makes it possible for an enemy to see a dropped weapon or steal it and use it against you, or switch to another weapon when they have no ammo left without me needing to define these things explicitly. Optimization techniques. Optimizing a game is all about maximizing performance by skipping any unnecessary operations. Rendering optimizations prioritize minimizing the amount of polygons, draw calls, and overdraw. One of the main rendering optimization techniques is culling. It makes the game not render anything that you wouldn't be able to see anyway, like frustum culling that makes the game skip things outside the camera's field of view, occlusion culling that skips anything that is behind a solid wall, cull, and backface culling that skips rendering the back faces of a mesh. Games combine this with a level of detail in the form of mesh LODs, simplified versions of a 3D model that increase in quality the closer you get to them. The lowest LOD a mesh can have is called an imposter, a flat quad with a texture that rotates to always face the camera, making it vaguely 3D from a distance. It's used to reduce the poly count of models. LODs can also be applied to AI processing, animation frame rate, lighting, and more. Basically, anything where you can afford to reduce quality without breaking the game. If you need to render thousands of meshes, your priority is to reduce the draw calls. So you would use something called batching that merges meshes together, or GPU instancing that allows meshes to have different positions but they must share the same material. Developers take advantage of this by using a texture atlas, a single image containing many subtextures. This way, the GPU can render everything at once, even if the subtexture is different because it's technically the same material, just a different region. In open world games, you need to use asset streaming that uses multi-threading to load assets in real time as they're needed instead of loading them all at once, and can include things like textures of different qualities, meshes, or portions of the map as you get close to them. This technology is the reason why modern open world games don't really tend to need loading screens. I'm sure there are more optimization techniques, but these are the ones used for the most common scenarios. Game engine controversies. At this point, every engine has had some sort of controversy. In 2023, the geniuses at Unity thought it would be a good idea to start charging developers up to 20 cents per game installation if certain thresholds were met. This applied for existing installations, not just new ones. Of course, nobody liked this, and the backlash was so strong, the CEO had to resign and Unity removed this fee. But the damage was already done, and many but not all studios announced that they would migrate to engines like Godot, which has also had a controversy because of a single sarcastic tweet mentioning the evil W word. That's it. Yeah, that's it. That's the war crime. To be fair, I think they could have handled it better. Many users were blocked from Godot's official Twitter account, and it led to the creation of the Redot engine. That is a Godot fork focused on apolitical views, stability, and performance. There's also been some backlash with Unreal Engine 5. It has many new features like Lumen that provides dynamic global illumination, or Nanite, a virtualized geometry system that lets games render high-quality models with millions of polygons without any LODs. However, many people blame these features or the engine in general for bad performance and a lack of quality in games, to the point many players associate UE5 with stutters, bad frame rate, and abuse of temporal anti-aliasing and upscaling, and claiming that these games quote-unquote look the same. You can see it online, with many users annoyed at studios that switch from their own proprietary engines to UE5. Some other people argue that it can be a good thing, as more developers know how to use Unreal, and that not all games made with it have technical issues. I'm going to be entirely honest, I've barely used Unreal Engine 5. I'm not going to pretend that I know better than the devs themselves, so if you're a developer using it, I would like to know your opinion. Do you think the criticism is justified? Do you think that it's a good or bad idea to switch to Unreal? Game accessibility. It's another aspect of game development that is often forgotten, but that lets players enjoy a game even if they have disabilities or certain conditions. It includes features like controller support, input remapping, color blindness filters, customizable difficulty settings, or closed captions. You don't necessarily need to have a disability to benefit from these. I personally can't live without closed captions in games, even if it's for the smallest things. If you're curious, there's this website called GameAccessibilityGuidelines.com that compiles a lot of features and suggestions you could add to your game to improve accessibility. Dead online games. When a company shuts down servers for an online-only game, the game ceases to exist. It's genuinely gone. There's no single-player mode, no way to play it offline, or to legally access it at all. Games like The Crew were delisted and made unplayable despite players having paid full price for them. Cases like these led to the creation of the Stop Killing Games movement that aims to preserve games after their servers are shut down by making the game companies offer an offline mode or to give players the ability to host a private server. But we'll mention this later. Private servers aren't really new and allow creating unofficial replicas of online games. For example, Turtle World of Warcraft, that offers a classic experience with expanded content, or those unofficial Club Penguin servers that keep the game alive. Some of these have had their own controversies regarding how user data is handled and just their overall legality, as it's common for private servers to receive a cease and desist. Though, in some cases, many game servers are basically dead, having almost no players, but the servers are still somehow running. I've noticed many people online that just find these empty places pretty unsettling. Floating point errors. All engines use floating point numbers to represent the coordinates of objects in a 3D game world. However, it's possible to encounter issues when the player has gone too far, especially in open world games with massive maps. Floats can only have so many digits, so at some point, the engine will not be able to store the exact value and will begin to round numbers, causing many issues and operations that need them, from rendering artifacts like z-fighting, flickering, or physics issues too. What most games with huge worlds do is to just teleport the world back to the origin if you're getting close to these limits so you won't reach them. Patents restricting game mechanics. Patented game mechanics can often affect the development of other games and limit innovation. One of the most repeated examples is the Nemesis system. Introduced in the Shadow of Mordor series, it allowed enemies to remember the relationship they had with the player and create some kind of procedural storytelling unique to each playthrough. But it was patented by WB Games and can only be used by them until 2036. It doesn't seem like they plan to make another game of these, so it remains unused, and most games that want this mechanic have to either find ways around the patent or just can't add it. If you've ever thought, wouldn't it be a good idea if games had minigames and loading screens, let me tell you that Namco already thought of that and made a patent, which is why games couldn't include this until the patent expired in 2015. But by this point, many games had already implemented streaming technologies, removing the need for loading screens altogether. Companies like Nintendo have tried to abuse this system to sue other companies such as Pocketpair, the developers behind Palworld, a Pokemon competitor. These patents were filed after the release of Palworld, and cover mechanics for capturing creatures by throwing an object, a creature mounting system, and a mechanic that triggers battles by launching a creature at another. Developing games for other platforms. All platforms have their own requirements and quirks. For example, developing games for consoles can require a dev kit, special hardware versions of consoles loaned to approved studios with debugging tools, unlocked features, and looser restrictions than the commercial versions. Getting approved to develop for a console requires certifications, specific optimizations, and strict NDAs. This is part of why some open source engines like Godot just can't provide tools to export to consoles. It's more of a legal issue rather than a technical one, and it's also the reason why indie games don't really release on consoles at first, unless they get successful enough to get a publisher. VR development also comes with some quirks that you don't really see that much in traditional game development. For example, the standard is to run games at a high resolution and refresh rate. A low resolution will make pixels very noticeable, and refresh rates under 90 Hz can start to make people motion toxic, so there's a lot of optimization involved. One of the techniques exclusive to VR is called foveated rendering, that tracks your eyes and lowers the quality of everything that you're not looking at. Some games might have to add support for certain peripherals that track different body parts. Many traditional game conventions have to be reconsidered from scratch. Engines like Godot even let you develop games while running the entire engine on your headset. And finally, there's a lot of things that make mobile game development its own thing. Most games follow a different business model. Instead of selling copies of a game, the standard has become to make all games free to play and with microtransactions or ads. UIs tend to be more customizable because you have to support more screen sizes, aspect ratios, and dynamic context. Optimization has an even bigger importance, as you have to make games drain as little battery as possible, reduce file sizes, and draw calls. Some engines have received mobile ports, allowing you to develop games on your phone, like Godot or GDevelop. Of course, it's not very intuitive, and it won't be the best experience, but I started by making games on my phone when I was a kid, and I would have loved to have these tools. It's so cool that it's possible. Controversial developers. There's been many controversial developers, such as Marcus Persson, aka Notch, who made Minecraft and sold it to Microsoft for $2.5 billion. He's posted a lot of inflammatory, inoffensive comments on social media, causing Microsoft to quietly remove his name from many of the credits, as they don't want to be associated with him anymore. Another controversial developer is Yandere Dev, the solo developer behind Yandere Simulator. That's always been kind of a controversial game, as you're a schoolgirl killing other classmates and has some pretty questionable mechanics. He's been criticized for a variety of reasons, from mismanagement of the game, as it's been in development for almost 12 years and it's still unfinished, getting assets from volunteers and being hostile towards them, having some excellent coding skills I'm sure everyone's so jealous of, to having scandals regarding inappropriate interactions with minors. All of these things have made him one of the most infamous developers in the recent years, causing people to make memes of him and even speedrun getting banned from his Discord server. A more recent example is Pirate Software, who became controversial because he heavily criticized the Stop Killing Games movement. His game Hardbound had a successful crowdfunding campaign, raising $20,000 back in 2017, but the game is still not finished and only has 3 playable chapters out of 5. Some people think that this is due to focusing more on his Twitch career and other projects. His coding skills have also been criticized, and he's just too humble. To be honest, I don't really feel knowledgeable enough to say much about them. I didn't work 7 years at Blizzard, so what am I gonna know? Tier 5. Labor exploitation. This is one of the most normalized problems in the game development industry. Crunch culture refers to the practice of developers working overtime, sometimes having 60 to 80-hour work weeks in order to complete a game. Many sleep at their offices and don't even see their families for months. Of course, this has a considerable negative impact for the physical and mental health of developers. So many studios have had controversies because of crunch during the development of games like Red Dead Redemption 2, Cyberpunk 2077, Anthem, or Fortnite. QA testers also tend to be exploited and underpaid, as companies take advantage of their passion, vulnerable positions in poorer countries, and many people still think that it's just getting paid to play games, when again, it's more about finding bugs, and it's an incredibly repetitive and tedious job. What makes it all worse is that it's become standard to have mass layoffs after a game is released. Some companies shut down entire studios even if a game was successful. Unfortunately, it is still uncommon to have unions in the industry, and companies like Rockstar Games or Blizzard have been accused of union busting. Lost games. Many games, especially older ones, are at risk of becoming lost. Many of these don't even have ports or legal ways of running them in modern systems, so you have to resort to resellers or emulation, which also has its own set of legal issues, and emulators are constantly taken down. In some cases, the source code of games has been partially or completely lost. Konami lost the source code for the original Silent Hill. It is estimated that the source code of around 90% of games released before the 2000s could already be lost. If you're a developer, you should archive as much as possible with version control and backups, even if it's a small project or if the game sucks. I myself lost the source code of one of my first games. It wasn't a good game, but it's important to archive them as they can be useful in the future for preservation purposes and also shows how much progress you've made. I was fortunately able to get it back, but not all cases have the same luck. Most games will fail. Finishing a game is an incredible feat and the hardest part of game development. Most developers have many projects they abandon for a variety of reasons. Even if you manage to finish your game, likely after years of effort, statistically, most games will absolutely fail. At least, most indie games will. Many estimations say that about 70% of indie games are commercial failures. Some don't even earn enough to break even or get back the money they paid for the Steam fee. So $100. Even fewer games will generate enough money to fund a second project. Most developers stop at their first or second project. It's a devastating but realistic fact. It's an oversaturated market and the odds are against us. Maybe my game will fail, maybe so will yours. We don't know. We can improve our odds with marketing, new innovative mechanics, a good art style and game feel, and other strategies. Still, nothing is guaranteed and we can only prepare, hope for the best, and learn from our mistakes. Censorship in games. Some platforms and countries tend to censor games. The list is very long, so I'll just mention known examples. Germany does not allow showing imagery from World War II, including certain symbols, salutes, and a mustache, so games like Wolfenstein have to be censored in this country. China tends to censor and ban games with violent or sexual content or that portray a bad image of the country. Australia also has a lot of strict rules and tends to censor for the same reasons. Credit card companies have also pressured game platforms like Steam or Itch to ban games with adult content, even if it was within the guidelines. Even if you don't buy these types of games, I just don't think someone should have the power to say what you're allowed to buy or play, because maybe today it's the games that most people don't play, but tomorrow it could be GTA 6 or any game with violence that's supposed to be for adults. Malware in game development. This is a topic developers should care about more. Depending on how some save systems are designed, a user with bad intentions could share a save file with malicious code that runs when another person loads the save file. This is the reason why you should really research before implementing a save system. If you're using Unity, don't use the binary formatter, as it's known to be vulnerable to these attacks. If you use Godot, do not use resources, the config file class, or the string var functions for save files. They're vulnerable to this too, and usually the best method is to parse all your objects to and from JSON. Speaking about Godot, back in 2024, Checkpoint Research found that malicious actors were misusing the engine to create malware. The hackers created fake GitHub repos claiming to offer cracks for paid software that once downloaded and extracted would use a Godot runtime and a GDScript file to download a payload. It infected over 17,000 machines, and potential versions for other operating systems or infecting other games could be made. If you think about it, it makes sense. Godot is free and open source, easy to learn, cross-platform, and has access to many system-level APIs, so it's a very convenient option for hackers. There's also been reports of fake developers asking if people can playtest their games on platforms like Discord Discord. When you download the game from itch.io and run it, turns out it was malware disguised as a game that steals your account and keeps spamming the same message to your contacts. As always, be very careful with whatever you download, no matter the operating system, who shared it, or whether it's a game, engine plugin, or whatever. Only download from official sources and scan files if necessary. Games development. This is a small rabbit hole of its own. First of all, these types of games are banned on consoles, so the only option is to publish on PC platforms like Steam or itch.io. Not all games of this genre are good, and it seems like it's even more common to have low-quality asset flips or games made with AI. Developers tend to publish their games under alter egos or studios dedicated to this category to be able to separate this work from other aspects of their life. It's a small market dominated mostly by indie games, and there's more to this, like players who make mods to hide the clothes of certain characters, add new adult mechanics, or unlock existing ones. This was the case of the GTA San Andreas Hot Coffee mod that unlocked an explicit minigame that was already in the game's code but inaccessible through normal gameplay. It became a huge scandal. The game was re-rated as adults only, causing retailers to stop selling it. Rockstar was fined and had to remove the minigame to be able to sell the game again. The Army's involvement in game development. The US Army has developed games. That was the case of America's Army, a free-to-play shooter for PC and consoles powered by the Unreal Engine that was basically a way of incentivizing gamers to join the army, claiming to portray more realistic strategies and scenarios. Apparently, the games were very successful and even managed to improve the impression young Americans had of the US Army by 30%. The latest game of the series was shut down in 2022, but it's known that the US Army still has some influence in game development and just gaming culture, having its own esports team and collaborating with studios to help them design assets, record sounds, develop VR technologies, etc. It's not really a new thing. It's known that this is a phenomenon that affects other entertainment industries too, like movies, shows, or music, but it keeps you wondering how much of the artistic vision or content in games is influenced by other entities like the government or corporations. Developers traumatized during development. I don't think video games cause violence or disturb people, but if you think about it, someone has to animate and design those violent elements in games, and this can often lead to animators and developers becoming desensitized or straight up traumatized due to high exposure to real graphic content. And this was the case of an anonymous developer who worked on the cinematics for Mortal Kombat 11. They had to be surrounded by real-life research material in order to recreate it in the game in the most realistic way possible, encouraged by upper management. The developers started having very graphic dreams, so they would keep themselves awake for many days to avoid sleeping. Eventually, they were diagnosed with PTSD, and they weren't the only ones affected by this. Some co-workers became desensitized and numb, and others had to leave the project. The Activision-Blizzard Controversies. In 2021, Activision-Blizzard was sued by the California Department for Employment and Housing. The claim was that the company had a very toxic culture where male employees came into work hungover, delegating unfinished work to female employees and harassing them with inappropriate comments, questions, and creepy behavior. Even executives and higher-ups at the company engaged in these actions without any repercussions. It is reported that a female employee ended up taking her life during a business trip with a supervisor who brought many adult objects with him. I spent so much time researching about this, and it still feels like there's always something else that comes up, and I just can't mention all of these things in this video. This case just shows how rotten and toxic the game development industry can be at its worst. Thank you so much for watching the video. It took me way longer than I expected. I had to balance working on this and working on my game at the same time. I'm sure I missed many topics and I must have committed a few mistakes here and there. It's a huge video after all, and I don't know everything, but feel free to mention your feedback in the comments. I think this is going to be my last Iceberg in quite a while. Thank you and see you in the next one.